Hi everyone, it's Nono here, and one more week I'm going to go through topics that range from creative coding, machine intelligence, art, and design. This is what I call the stream Nono.MA live, and today we have a specific topic which has to do with machine learning. Is t-SNE or t-SNE. This is an algorithm for dimensionality reduction that we're going to try to use with Sci-Kit-Learn. For those of you who are connecting with us for the first time, this is me, Nono Martinez Alonso, connecting with you on Thursday afternoons here in Spain. So this is from 12 to 2 p.m. EST, Eastern Time in the United States. And I just try to go through things that are things that I want to learn myself, like creative coding or machine learning or things like this, or things that I already know that I want to show or I want to record tutorials on. So this is a space where I get to connect with you and we have time to learn together in some way. So I'm going to get started pretty soon. I don't want to take a lot of time with the intro today. I want to get right into the code and show you also something that I have here that we've used on other live streams that they just updated. So I will ask you to vote on the poll if you're, what topic interests you more on the chat, and to let me know on the chat as well who you are, where you're connecting from. I'm also important. Let me know if you can see me okay and if you can hear me okay. All right, let's get started. This is live stream 38. I would encourage you to like the video if you want to support my channel, if you want to support the work that I'm doing here, and subscribe if you think you're going to like the content I publish in the future. Click on the bell if you want to get notified when I go live next or when I upload new videos. You can also join us, join the community. There is an invite for you at Nono.MA's Discord. You can also click on that QR code up there with your phone. And a reminder, last week we didn't see machine learning. The live stream was about HTML5, JavaScript, and web components. We did a flex grid with HTML5 and CSS, and we also made a dynamic view component, which was a grid view that turned into a list that could also be sorted by different properties, say time or name or numbers alphabetically. We didn't get to Sci-Kit t-SNE, and I promised that in a future live stream we would focus solely on that. So I'm going to try to do that. I'm going to try to focus only on Scikit-Learn and t-SNE today. I see Sajed is online today. So hi Sajed, thanks for confirming the audio and video is good. And as a quick announcement, we released last week or 2 weeks ago, we released the free diving episode of Getting Simple. So Jose Luis Garcia Castillo and George truly talk about the mindfulness of breath holding diving and being deep underwater, best practices, equipment, techniques, equalizing your middle ear pressure, scuba versus free diving, and recommendation systems. I believe this is a really good sport if you're looking to train your, physically, your body, and also your mind. So it's mental and physical. And yeah, I'll invite you to listen and tell me what you think. It's a short one compared to others. It's 25 minutes. And hello, John Mark. Also, nice to see familiar faces online. Glad that you passed by and said hi in the chat. All right, so you have a door open to ask questions about this or previous episodes of the podcast at gettingsimple.com/ask. And we're going to get right into today. So today, as I said, I don't know if we'll have time for other things, but for sure I want to get started with the Sci-Kit t-SNE project or exercise. This is the cover of this, is Dimensionality Reduction with Scikit-Learn t-SNE. And we have some material. So I'm getting material from Hands-on Machine Learning with Scikit-Learn Keras and TensorFlow book by Aurélien Giron that I'm encouraging you to get or like learn from if you want to get into machine learning, specifically about chapter 17 that was auto-encoders and GANs. This is something that we did on live streams 34. I don't know if 34 and 35 or 33 and 34, but you can go back. They have, I think they have chapters, and these are the ones that go through how we actually build an encoder, a decoder, and how we stack them together. And there is a lot of theory there that, or even hands-on practice that we learn from. This is, there are many ways in which you can do these stacked autoencoders, but long story short, you try to input something and get the same in the other way, but on the way you're training an encoder, so you're obtaining these codings on the right, and then you have another second part of the network that is a decoder, which from those codings tries to regenerate the original output. These are networks that are mainly used for noise removal filters, not for generation, because the output are usually noisy. But if you get GANs on the game and other types of networks, these are good architectures for generating images. We saw how to do this, I believe, in live 35 or 34, how to get a network that could learn how to generate these images from this image. And what we want to see today is this part here. So this is what we would imagine that we can obtain. This is t-SNE flattening a highly dimensional space. We have 30 digits or 30 codings of 30 digits, I think, on the network that we coded back in previous live streams. And with this library, so with the t-SNE library of from scikit-learn manifold import t-SNE, and this is really pixelated because this is a really bad image, but I have the book here with me. So yeah, we're going to try to visualize that here, and I'm not sure if we're going to be able to get these big images here by automatically. I think maybe we are, but yeah, we'll see. So I think that's it. So we can get started with coding now. And one thing that I'm going to show you now. All right, so quickly turn over to the chat here. John Mark says, I like the freediving too. A bit far from the sea right now, but compared to Scuba, I enjoy the liberty. Yeah, I actually haven't tried. So this is kind of commenting on this. I actually haven't tried scuba diving. So actually diving underwater with an oxygen bottle. I've only done it snorkeling or with free diving techniques, which is with like a lead weight belts and other things that let you go deeper underwater. So the one thing as a pointer that I think I showed last week on the sketch.nono.ma site, if you go there, I have a few stories. So this one that was auto vent, this one is first impressions, this one is how to prevent your diving or snorkel mask from fogging up, and then this last one that is the diving reflex. You have a few short essays or publications that talk about my experience free diving or some of the concepts that I've learned. You can go back here. So blah blah blah. Yeah, there are a few back. Yeah, so these ones. So this is the ones that I was mentioning before. All right. And yeah, I think that's it for kind of the plug, or like showing some of the things that I've been writing lately. I see also Class says, hi Nono. Class, I believe I haven't seen you on the live stream before. Maybe you can tell us how you found the channel, or why you're connecting, or where you're connecting from. All right, so I said I was going to show, so we were at this Let's Code slide that is kind of what we're going to start doing now. I have something here on the right. This is something that I've used before on the live stream, but that I want to show today. So one of the sketches that I had on my site was this remarkable tablet that I hope you can see there, right? So this is the Remarkable 2 tablet, and they just released a beta feature today. Like I discovered it like 5 minutes before going live, and look how awesome this is. So now I can sketch here and take notes on like a whiteboard style, and you can see that live, right? Now I can go here and I can erase all, and you can actually see, so this is a new feature that they called screen share, which before you could just see like some sort of live beta view, but now you can actually see me drawing live. And I haven't tested yet what would happen if I set to landscape view. Yeah, this is probably even better because we get it zoomed in, and I can just put it like this, and I have a canvas board. All right, so I see also I'm from India. Okay, so hello, I can put here too, and we have here class from India, so seems to be like a new subscriber, so welcome. And Ricardo from Brazil. I'm your new subscriber. Well, welcome. I hope that you enjoy it. Today we're gonna see a lot of machine learning, or at least a bit with t-SNE. So let's take a look. And you know, the poll is open. I don't know how many. Yeah, 3 people voted. It seems like everyone wants to see t-SNE. I don't have another great alternatives, but I'll try to do that moving on. So in future live streams, so we get this sort of polling system where we can go between different choices, and you guys can be the ones that pick one or the other. In this case, the one that won is t-SNE. So this is also just to encourage you to be live at the beginning of the live stream if you want to kind of participate in choosing the topics that we're going to discuss during the live stream itself. All right, so things that we have that I'm going to go to the just record an intro screen for this, so we have it later for in case we edit a tutorial, and we'll get started. Also, a question that I'll ask while I'm recording this: anyone has played with t-SNE already, with scikit-learn with t-SNE? Because I'd like to know if you have any insights or any comments that you can do there. Hi everyone, it's Nono here, and this is a hands-on tutorial on dimensionality reduction. We're gonna try to do that with scikit-learn and the t-SNE implementation that comes in this package. We'll try to get the codings that we've obtained from another neural network, put our dataset inside of scikit-learn, and try to reduce the dimensions of our dataset into 2D. So we can plot it into a 2D map or an image, and we can understand the similarities or how our dataset looks when you compare one input to the other, or one data sample to the other. It's Nono Martinez Alonso here, so let's get started. All right, so we're going to now record an outro just in case I forget that as well. But yeah, I don't know how long this is gonna take, so okay. Thanks a lot for watching. It was Nono here, and we'll see you next time. All right, so I see I want to know nothing. I'm importing cafe, but it's showing this error cannot parse. Yeah, so clues for questions that have not too much to do with the topic that we're covering today. I would encourage you to go to the Discord server, so you can join the community. You can ask on probably this is good for the coding channel, the code channel. You can go into that QR code or at Nono.MA Discord, and you can ask those questions there. I don't think I can help you today because we're going to focus on a different topic. And yeah, maybe you can do that. I'm not sure. All right, so let's get going with what we were going to do. So this is the tutorial. All right, so we have this canvas here, and I'm gonna do a recap of everything we know and everything that I expect to do in the next hour. So let's see if I can center this thing here. All right, cool. So things that we know or things that we already have on live stream, and I have to check there. How can I do that? Yeah, so live stream 35. Yeah, so we generated this data set, and I believe live streams. Okay, so in live stream, so live 33 and 34, we did see stacked auto-encoders. We made, I believe, 2 versions of a Colab notebook. And in there, we were actually having that architecture in which we were taking in an image. So that would be like maybe a PNG. I think that was 28 by 28. We were encoding that into 30 digits. Right, so these were the codings of our network. And then we were getting that back into another image that is 25 by 25. That was the reconstruction. And this was our input. So we try to do here is to train this part, which is an encoder, and this part here, that is a decoder. What the encoder learns how to do, right? So the encoder learns how to take an image, so whatever it is, and it's 28 by 28, which is 768 pixels, into a 1D tensor or array that has just is 1 by 30. So it has 30 digits, right? Or pixels, whatever you want to call it. It's just 30 digits. It's not pixels, because here actually we have RGB, so 3 channels for each of those pixels. All right, so we're trying to get, and I'm going to go to the next page now. So we're trying to do is, I'm trying to get a network where we put an image, right? So we have our network here, which is a decoder. And we're going to get, so this is our input, and this is our codings. And those codings that I mentioned are going to be 130, so 30 digits, will then input into t-SNE and are going to be able to plot on a 2D image. And hopefully we're going to get clusters that belong to different classes. So for example, this could be type 1 or type 2. The problem is that so the data set that we're going to use, those sketches that I showed before, those don't really have a, like, we don't have a classifier to classify them. So we'll just see how the data samples look and similarity between them. So we're just going to try to do that. Let's just add here live 38. So this is live 38 and it's 22nd of July. All right, so I'm going to read here the comment from Ricardo. So I've already used t-SNE. Let me see. Oh, message retracted. I was going to read it, Ricardo, but you deleted it before I could do that. So if you want to rewrite, if not, it's fine. Up to you. Now I'm curious about what you were going to say, that you've already used t-SNE. Okay, so let's keep going. So the first thing we're going to see is, like, we're going to take a look. So this is again live 38. Maybe we don't need to write the date all the time. And we have a set of 105 images. We need to recover our notebook, and we need to make a new one, new notebook with scikit-learn. Right, I think I can even zoom into here, right? Awesome, cool. So let's see. So I can, yeah, let's do that. If you have any questions, if you're live, feel free to put them on the chat. We're gonna get started right now. Great, cool. So as I said before, I have this data set. So we have 105 images from my, oh, let's actually stop Dropbox to make sure that this doesn't slow down the computer. All right, so Ricardo was curious about using the t-SNE with convolutional neural networks and make t-SNE plot instead of images in the plot to plot colored data points in an unsupervised way. Data points in an unsupervised way. Can you elaborate a bit more? Would that be like things that the network is learning? I'm not exactly sure how that would like. I cannot imagine it. And maybe that's what the exercise you're proposing is about figuring out what it does. All right, so this is a data set, and this has 105 sketches from the website. So we have if you go into the live repository, so this is the repository of the live streams. In live stream 35, you have a TypeScript script that will guide you step by step on how to use an asynchronous pipeline to download those images from my RSS feed that is here. But you can actually change the URL of the RSS feed and a few properties to download images from another source, right? In this case, we were just getting the images from here that, show you that here. Funnily enough, this is a remarkable tablet that I was using with this application here to share screen. And yeah, so you can go there to take a look at that. And I don't think we have more things here on the repo. The algorithm that we're going to use, well, I was mentioning we have these 105 images. These ones are 2,500 pixels height and width. And if I go here to sketches 28 pixels, right, you see that these images are super small, so much as we cannot understand them. But if I make them a bit smaller, you start trying to maybe make sense of them. And here we have a collage of all of them, right? So the purpose of having the images down to 28 pixels is to be able to put them into the Keras model and have the training be a bit faster. And yeah, so class thinks that what Ricardo is saying is right. I'm not understanding it fully yet, but I will at some point. So we have this data set, and this is the data set that we're going to use. We have to, challenges that we're going to have to face are, so let's see. So format, data set, train, stacked, auto-encoder, data set conversion to codings, and then our codings are gonna go into t-SNE, and then plot them. All right, so let's see how fast we can do this. Okay, so let's go back to our notebook. So for this, I'm gonna open colabresearch.google.com. This is the website where we can access the notebooks. And I believe on Discord we have the links for last for the previous live stream. So we have the links here, so we can maybe make here links for live 38, and we'll start adding things here later. So here we have the stacked autoencoder part 1 and part 2. Maybe this is part 3, I'm not sure. And I'm gonna sign in with the account that I created for the live stream. All right, so we got Google Colab here, and we can now access the stacked autoencoders notebook. So this is gonna be I'm gonna make a copy, so save a copy in Drive. You know, I'll be, Ricardo, I'll be interested in seeing some of the things that you have been working on. Maybe you can share them with us at some point on the live stream, or in some other form. Okay, so all right, so dimensionality reduction with Sci-Kit-Learn. We didn't end up doing that last week, so we're gonna update this notebook. I think this is my notebook, and okay, so here we have the copy of the previous notebook that we might not need. This is live 38, and I'm gonna put the same here, so live 38. Okay, so now that we have this, let's see what parts of the code we need from the previous notebook. So okay, yeah, so I think Ricardo, I think what you're referring to what you might be referring to, and I'm not too sure, right? When you have data samples, some algorithms like support vector machines, for example, you have different clusters of data, and this type of algorithm might automatically, or in a unsupervised way, as you're saying, might separate your data into different clusters, right? So without you having to specify them. So this is like unsupervised clustering algorithms. It's kind of like KNN. But yeah, let's see. These are super interesting questions and comments, by the way. All right, let's try to continue here. The first thing that we have is that we have the fashion MNIST dataset, and I want to do this with our own data, right? So what I'm going to do first is I'm going to add a text block here. I'm going to say load custom dataset, and this is like images are 28 by 28 pixels. RGB. Okay. Then the second thing that I said is that we need to define our, maybe let's make this bigger. Define encoder and decoder. Define stacked auto-encoder. Then train model. And later would have to encode entire data set, and then we'll have to Reality reduction with this, and you know, these categories might change, but at least we have placeholders here. All right, so first thing we're gonna do is I'm gonna import TensorFlow as TF, and I'm gonna import well, I'm gonna leave scikit-learn for later. Let's take a look at what we have. So we have TensorFlow 2.5.0, we have Python 3.7, we do have a CPU, and we don't have any GPUs. We can select a GPU here to make our notebook faster. So this is now going to allocate it for you and initialize a new runtime. So now we run this again. We're gonna have the same version of TensorFlow and Python, but now hopefully we'll have a GPU. All right, so now we have a GPU device. It's a Tesla T4. Okay, great. So where do we have our data set? How are we going to put our data set here? And maybe the easiest is that we just drag and drop, because this is a really small data set. The problem is that this might, you know, require that we do that every single time that we want to do this. But I'm gonna go with that route for now. So I'm gonna go into this sketches folder. I'm gonna use this script to zip my file. So it's just I go into the folder and I just call this, which is just zipping the file with the same name that the folder has. So maybe we just call it sketches, and this is 352 KB. So this is super small. So we're going to simply drag and drop that into our notebook. A reminder that files will get deleted when the runtime is recycled. So if you close your notebook, go away, and then come back, the data there is not going to be there. So there are ways in which you can download those files, or maybe download them from other source or upload them somewhere. So if you look for, I think, I don't know if this is going to show up. Yeah, so I have a video on how to, oh, this is old, man. I have a video here on how to auto download files from Google Colab. And this is something that I really like, because that way you can run your notebook and then your files end up on your downloads folder and you don't have to worry about that limitation. All right, so now we have this here, and I guess we could unzip them. So load custom dataset. So we're gonna do some preparation here, or maybe load custom data. So we can do here. So we can, let's see what folder we're at. So we're on the folder we're in the content folder, which is this one here. So we can do unzip sketches.zip. Let's see what happens here. So I think all the sketches might go to this folder, which is probably not the best. But yeah, I mean, we have them all here, and they're JPEGs. Cool. If we put here the queue, this process is silent, so we don't see anything. except for that. Zip terminal replace, yes. Well, one thing that we can do to avoid these sort of questions is we can just say remove all the JPEGs in this folder and then unzip. That way everything gets removed and then unzipped again. Unzip, terminal, unzip in folder. Right. So we can specify here to unzip on sketches. That way we unzip to a directory instead of to the main folder. All right. So now we have our 28 by 28 pixel sketches here, which is our data set, which is super small. Now we need to see how to load that in the same data format that we had our data set on the previous live stream. So this notebook here, you can see we're downloading with this function here. So tf.keras.datasets fashion MNIST load data. This gives us data in a really specific format. So in this format here, so 28 by 28 pixels, and they're 55,000. So we want to get our data in this same format, but in having less of them. And hello, Bea. Nice to see familiar faces. And what we have here is automatic. So what we have right now is we only have 105 samples, which is going to overfit a lot. And this is not something that I had thought of, but at least we can set up this notebook and then we'll use it better. So we will load all of our data. We have X train full, Y train full, and there's the test and the test. Okay, so let's just debug here the data. Oh, maybe not. Cool. So let's simply try to load our data with TensorFlow. And I don't remember right now where I have that. Let me check. Well, this is one way, but I think there should be better ways. So we just load what I'm showing here is loading the images with Peel, but I want to load them directly with TensorFlow. I don't want to load them with Peel. Let me see. Actually, let me just take a look at the book, just to see if there's something useful here that we could use. K-means. There is an algorithm here that is doing K-means and actually seems to be similar to what we mentioned before. Class says, I want to know how many conv2d layers should we set without hyperparameter optimization. That's a good question. I'm also trying to learn. That's like neural network architecture, right? Like to try to identify. It really depends on the task you're trying to do. And I'm no super expert. Let me check here. I'm just trying to see if there's like oh, if there's like a section where we could see those things, but yeah, that might take more time. All right, so let's say here TensorFlow load image. Yeah, so yeah, they use pill. I don't understand. You can probably okay, let's try this one. Let me take a look at something here. All right. Okay, let's try this one here. So dataset list files string data there. So data there. Where is data there? All right, so let's take a look here. So just to see if this works. So I'm gonna import pathlib, and I'm going to call pathlib path sketches, and then here we're gonna do data there, and then our pattern here is gonna be just everything here with JPEG. All right, let's see if that executes. All right, so we get shapes, types, strings, and this was good before, just that I don't think we even need these things if we just put here sketches, but let's keep it for later just in case. So I think I was doing something okay here. The problem is that these are strings and they don't have a shape, so we could say for image in print image, let's see. All right, so we're actually okay. So I was a bit confused because I wasn't seeing the shapes, but this was actually working before. So what we're doing is we're listing, this is sort of making, well, sort not, it's actually, if I do here train files and print, so we just do this, right? So what we have here is a tensor slice dataset, which, you know, doesn't have any shape because the type is string. And with those train files, so we can say here train files, and we can say here file, we can print the file. And yeah, again, we get this binary string here that is just the path to the string. So we need a function now to decode those images, right? So decode JPEG, I'm going to use a helper function that I have here. So we're going to decode, we're going to define a function that is going to decode an input image, and we're going to convert the compressed string to a 3D uint 8 tensor. So image is going to be, let me see. All right, so first we need the load image train, right? Okay. Okay, so we're gonna do here two helper functions, but at the end of the day, what we'll end up doing is that we're going to need to do this. So we're gonna need to call on train files, we'll map, and then call a function that we haven't defined yet, that is load image train, and non-paralleling calls, we're gonna use auto-tune. All right. And of course this is going to fail because that function doesn't exist. And what we can do, let me just take a look here at the chat. All right, so there are no comments, so we're going to end the poll. So we have 4 votes here, and great. All right, so let's keep going. So we're loading the data set, and we're going to define that load image train function. Load image is this better? I'm not sure. Load image train, and we'll get the, I think we just get the path. Yes, so we get the file path, and what we do is that input image is gonna be, we can do read the file, so the file path, and that input image, we're gonna decode our input image, and we're just gonna return that input image. And you know, we could do other processing here that I'll show here. And we need now that decode input image function that I was going to define below before. All right, so here we would decode input image. So we're gonna get tf image decode JPEG with that image data that we've obtained, and we have 3 channels. What this is doing is that we're converting the compressed string to a 3D uint 8 tensor, and now what we do is we convert to floats in the 0 to 1 range. So we use tf image convert image d type, and we get tf float 32. And now we would maybe here resize the image, right, the image to the desired size, which, you know, it's going to be here 28 by 28, but the images are already that size. But if we do this, then the dataset doesn't need to infer the image size, and we can do other operations, right? So we can do here image width and image height, and anti-alias, we can choose here either true or false. All right, so a hyperparameter here, we'll put here our settings, and we'll put here image width equals 28, and image height is going to also be 28. So we load that. Great. Cool. So where are we? All right, so we're here, so we're loading, and then we resize the image. So this should already work, right? So we're printing that, which means that we're going low. We don't need this, and we don't really need this or this. All right, so now, so let me go back here. So this is going to be the train data, which, you know, we don't really have test data, so we might need to do some split later. But for now, let's see what we got here. So we got this train. All right, so we have a parallel data set with shapes 28 by 28 by 3. There's one thing that is different here from the previous, right? So we, on the previous live stream, we were getting this shape, right? So we were actually getting just black and white. And maybe that's something that we could do here with Keras. We don't really want the images. Well, I mean, we do want the images to be black, to be color. But maybe that makes this problem a bit more complex, a bit different than what we had before, and we'll have to change the neural network architecture. So we have 28, 28, 3. These are the shapes. Train. I don't know if I can. Okay, so we'll have to get a subset of the data set. So we'll get. So let's see here. All right, so we can do train take 2, 3, for example, for image in blah 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 print image. All right, so we actually get the shapes, and maybe we can even print here the shape. No. Parallel map take to tensor. Let's see. Not sure if this works. All right. Cool. All right. So all right, not sure. Okay, so this is a problem I've seen before as well, and I never know how to properly work with this dataset objects. Right, but what if we do a train data set and we run train, cache, shuffle, buffer size, which we need to decide, batch size, p. All right, so this is going to ensure that we have more data samples, and we now need to define these two hyperparameters. So let's say our batches are 32, and we're going to see now if this gives us something different. All right, so repeat dataset shapes, none, blah, blah, blah. So this means we have as many as we want. So we can now do for sample in train dataset, take 128. Well, let's do just 34. Print sample shape. All right. So we're getting batches. So we're batching these things, and so let's say we just get, right, so 32 multiplied by 3 plus 8, that is 104, right? So all we can get here is these 4 batches, and then we reset because we only have 105 samples from the dataset. So they shuffle and then they start again here. So because 105, we cannot really, well, 35. So our batch could be, for example, 35. And now maybe we still get, oh, because of the buffer size, 35. Right, now we get, we still get 34. All right, let's actually leave it here. So this way we can get many different batches, so we can say 10 batches and we'll have more samples here. And we don't really need this data batched, but what we can do is that we can put here the possible processing that I mentioned before. So if we get for each of these, all right, so we have an RGB image. One thing that we can do here is so Keras to black and white. The RGB to grayscale. So we can actually convert to grayscale. So tf Keras image RGB to grayscale image. All right, let's try that out. Now we do have the shape that we wanted. So now these are going to be the same proportions. So 28 by 28. Let me see, can we do this? Can we? Let's run before. All right. Can do this with same session. I'm not sure if the sessions are via IP or I want to use Cafe model, how I can use it in Google Colab. Class, I started playing with Colab Pro this month and it is worth every penny. Highly recommend. Last run, I could train a model on P5, 16 gigs for 24 hours, no stopping. Yeah, so Cafe model, I'm pretty sure that you can, well, I don't know, run Cafe model Colab. Well, it seems like here's a way to do that, but I'm not sure. I've never done it myself. Okay, let's see what this data is all about. Okay, actually I just thought we can, just for testing, we can bring this all to the other notebook. Let's just try to debug with this. All right, so we have this here. Okay, import, maybe import numpy as MP. Great, and here we have, for example, X-train full shape. Okay, what is this like? So this is like 6000 of 28 by 28. So if we get the first one, what's the shape? 28 by 28. And if we print it, 28 by 28. So there's like 28 items of 28 digits, right? right? So oh, how many commas? 27. Yeah, they're 28 digits. All right. How can we reshape if we do have something that is like our data, right? So we have here this sample 28, 28, 1. So this means let's just print it. So let's take this one batch. Okay. So this is the opposite of expand dims. Unit by 1. All right, easy, great. Okay, so we have this sample now here that we've reshaped. So cool. So we get 10, we just get all of those. All right, so we have a way in which we can do that. So we probably want to, because this is returning the images, and here we're decoding the input. So maybe input image, here we do the reshape, and we say that our input image is going to be reshaped to 28 by 28. Let's see if this works. All right, nice. So now we don't need to do any reshaping. So we just print the sample shape, and our data set has a set of images that are 28 by 28. And I guess individually each of these is 32 by 28, 28, which we saw up there. That was what's the shape of this? 28 by 28, and the full is 6,000. All right, awesome. So we're loading our data set. That's good. So we're loading our data set in a good way that we can now use it. Just as a recap, for those of you who just connected, we're trying to load a data set to do a dimensionality reduction exercise with the t-SNE implementation that comes with Sci-Kit Learn. And you know, we've gone, we're trying to be here, so we're on this push button to connect. Okay, so we're trying not sure, this might have gotten disconnected. Okay, back now. Great. So we're trying to do this, right? So format the data set, and later we get time, we'll be there. But you know, we'll have to continue with this series. I don't know how to make sure that this is something that we can finish. All right. So we're loading these images in 28 by 28 size, so two really small to see with your eyes, right? These are super small images that are pixelated, and we drag and drop those to here as a zip file. So we unzip that with here. So we unzip those files. All right, so probably we can run this now. So this removes the folder and then unzips, right? All right, so great. So we load the data set here. We actually don't need to do this here. We can put these functions. Hello, Lourdes. Nice to see some familiar faces online. Great. So we have the data set here. So we're loading that data set, and here we can load a set of things. So if I do train data set take 10 and I get the first one, let's comment this out. Take dataset is not subscriptable. All right. All right, let's actually look for that error. Tuple. Is that a hack? Tuple train dataset. All right, so, or maybe we made that on an object that is not gonna end up anytime. So maybe just make it into, awesome. So let's see, shape. Convert to tensor. All right, I don't know if this seems a bit like a hack, but I might get there. 2, maybe not. All right, all I'm trying to do is get the data set that we have here, right? So we have a data set, and if we get let's say this is actually a batch on our data set. So for image in batch, we can print the image, and maybe we just take one batch, right? So we have the image shape is just 28 by 28, and we could actually plot this, so just to visualize it, but we're not going to do that right now. All right, let's see what we can get. So I'm not sure if I can do here a prefetch. Okay, so here I'm getting at least a batch, so we can say, can I get just the first batch? All right, I think this might work for now. Right. TensorFlow dataset to NumPy array. I'm really always confused why all of this doesn't really work. NumPy data. From tensor slices. Train dataset. Shuffle batch. I don't really understand. I mean, we're probably able to simply use that. All right, so we have the data set, so we have the train data set, we can train with that, and it seems like that's gonna be okay. Let's take a look. So where are we? So we have to, so format the data set. I want to get at least a few inputs loaded manually. So I would say load image train. So let's say we just load the data manually. So load images manually. We've been here for half an hour trying to do it in a different way. So I can say import, from pill import image, so we can do import glob, from glob import glob, I think. So we do glob sketches, we get all the paths, right? So for file path in this, we can say our image is going to be image open file path, and we can print, for example, the image width. Fill image size. Okay, so maybe just lowercase. All right, so it's 28 by 28. That seems to be right. Well, once we have the path, actually, even if we don't use pill, we do have this load image train, so we can do image equals load image train, and then we put here the file path, and then we can say print image shape. Right, so we get images that are 28 by 28 as well. So we could say, okay, our, like, let's say X train full could be that, and we just do X train full append and this image, and then we print X train full shape, which I think we need to make into an MP array. Right? All right, so we do get the shape that we wanted. We don't need to print here, so we're just appending. We don't need pill. All right, so this is what I wanted to do. I didn't want it. I wanted to try to do it with the tf.data library. And once we have this, these are also black and white. These are the type that we wanted. And so we could say data. So this is, so our data is going to be this, right? And then we can say, okay, we have data on the shape of this. And because we don't have more data, we're going to have to say X train full is going to be so 105, well, 104. I'm not sure why it's 104. Yep, yeah. So we do here data, and we get the first, so 104 multiplied by 80. So let's do 80%, so 84, for example, and do like minus 84. So we leave 20 X valid, and we just want to see the let me just close everything here. We just want to see the validation is the same. All right, so X train full is going to be just is the data, and Y train full Y test. I don't think sure what the Y is here. All right, so X test is type. Okay, that's important. So we get here, we get the X train full 0. They're already converted to D type. That is what they're doing here to flow 32 divided by 255. That's what we were doing here. So we don't need to do that. So all the data is all the data. And now we have X train, Y train. So we get here X train, and where are all these notebooks? Right. X train full. Let's test this out. Okay. Okay, so let's see. So we're gonna get here minus 20 data, so X train full minus 20, and this would be X valid, and we'll print here X train, X valid, the shapes, shape. All right. Train, probably the other way around. All right, so we got the entire data set is this shape, then we have all the data, and then we have the training and the validation data set. Cool. Right, so we have a data set now, and we can get the encoder decoder architecture. So we're going to copy and paste here for expediency, otherwise we're not going to get there. We have the encoder and we have the decoder, and we have the stacked auto-encoder, which we're going to paste here. We can go probably another day a bit slower. Awesome. So we have our stacked auto-encoder, and now here we defined it rounded accuracy, which is our custom metric. We compile the model with binary cross entropy and this learning rate and our custom rounded accuracy metric, and I'm going to make sure that this is working. Share summary. Okay, we can print the summary, and let's see what's hanging in there. What's going on? Okay, we can actually, something is weird. TF is not defined. Okay, so we could run everything above this cell. So run before. All right. All right. So I see some people are connecting now. So for those of you who are new, or those of you who were not here before, we're going through a dimensionality reduction exercise with t-SNE. This is an algorithm, an implementation of this algorithm in Sci-Kit-Learn. We're trying to get there. We had to do a few stages to get there. So one was to format our data set, Another one was to train a stacked autoencoder, which we're doing now, and then later we'll see how to convert our dataset into codings, those codings into t-SNE, and then plot the samples. And we seem to be running a bit out of time. All right, so let's leave this here. And yeah, I would encourage you to say hi on the chat to tell us where you're connecting from and what you're looking for to learn from this channel. All right, so TF is not found, so let's execute this cell. So we have our autoencoder, we define our metric, compile this, we get a summary of the model, and we have to train now. So now we can train with our data. So this is the actual cell that trains. We're going to train for 10 epochs, and you see that the input and the output data is the same because we don't have, you know, we're trying to, if we look at this image, right, the input and the output are the same. So the goal that we're trying to reach is the same. So we use the same input and output data set when training. All right, so this is super fast. So maybe we can train for more epochs. Yeah, it seems we might be overfitting there because we don't really have too many samples. We just have 104 images, but you know, maybe we get somewhere. Okay, so we have gone through this, and now we need to see if we can get the codings. This is a bit hard. So for me to understand the other day was a bit hard. So we could get a subnetwork of what we had before. We have our encoder, and so I believe we can pass an image through our stacked encoder. So we could pass x train 0. They put 0 there is incompatible. Let's see, expand dims. All right, so if we pass the image through the stacked encoder, right, we're passing the first image on our dataset here, we're getting the codings, which are 30 digits. And what I'm not completely sure, so this is after training 40 epochs, let's say. If we retrain, let's say we retrain for, well, if I retrain now, I think continue from where we were, so we have the same accuracy. So we might need to reset our model here and train again. Right, let's train again. So you see the accuracy starting from, or the random accuracy starts from 53, 70, and 96. We get really fast, we get really high. So I'm just gonna put here 1, so we get just to this step, and I'm gonna go through all of the cells again. All right, so we have this model here, and this was with 40 epochs. We're gonna try to do it now just with 1 epoch. All right, so the encoder network, right, which we defined here and we included here in the autoencoder, has actually been trained and its weights have changed. So we, when we run this feed method, the autoencoder has inside the encoder, and we actually have this network here that can get this image, right? This input image that is 28 by 28 image, and then generate the codings. And what we have here now are 30 codings, right? Like what we talked about before. Let me see if I can reconnect. Yeah, so we're reconnecting here. So these are those 30 codings, right? We were talking about a 28 by 28 image that was passing through a network. So we were training in this loop of encoder decoder, and in the middle, this encoder part ends up with 28 by 28 on the left and then 30 on the right, right? And we are actually seeing that here. So we if we look at the shape of X train, so we look here, it's 28 by 28. I put it through the encoder, and as promised, if we get the shape of this, I'm not sure we can do that. Yeah, it's 1 by 30. So it's a linear tensor that has 30 digits inside of it. And, you know, promise achieved, right? And if we change the input, so I'm taking different images here, the codings on the bottom slightly change, right? They change a bit because the input is a different image. They're different, right? So 173 and 152. So what we're gonna do now, just to prove that that's true, is that I'm gonna go to 15 epochs and I'm going to rerun these cells and retrain, right? So we retrain there. Now our render accuracy is again at 98.16, which I believe is the same that we'll get if we go to 40 epochs. And what I'm going to do is that I'm going to put here 15 epochs, but I expect to see something similar to below. And I don't. Let me see why that is. I'm not really sure that all of these things that I'm saying are true or not, but I'm trying to get there to understand everything. Okay, let's train again, because I said 40 epochs, but that wasn't really true. And rerun this. All right, not really getting there. Okay, let's do actually, so 40 epochs. So let's do actually 10 epochs and redefine everything from scratch here. Right, so that's 10 epochs. And I'm going to put here 10 epochs. Right. And now we're going to put 40 epochs. And I do think we need a larger data set. All right, so 40 epochs, we run this, -1 everything. I'm unsure what's going on. So how can we see the weights on the layers here? All right, so I have a way to plot the codings. And well, one thing that we can do is that if we run this by the stacked decoder, right? So if I now get this output from here, so let's say that the codings, and I run this, my print codings, you see them. So now I can pass the codings back here, and we get back, so this is a generated image shape, right? So that's again 28 by 28 image that is black and white. And if we get the first one of that batch, we get an image. So let's take a look at how to plot those, because I have the code here. So plot image, we have a helper method. Plot image, show reconstructions. All right, we just need to put this helper, and we'll have to do some cleanup. I'm not gonna do it today, but we'll have to do some cleanup. All right, helper here, so we can plot the image. And I'm not sure if this changes anything. So if I do here predict, I get a tensor, and then if I do predict, I get something different, but it's at the end of the day is the same result. And then I get an array as well. All right, so we wanted to plot this image, right? So we're gonna plot the generated image. Let's see what that does. Plot is not defined. All right, PLT. We have another dependency, and then we go back, and we got our plot image. All right, so it doesn't really have predict valid 0 plot image. All right. So it seems like it's learning something, right? So it's learning something. We got the input that we're using here. We can also plot it. Right, this is one of the, this is the input that we're inputting to the network, and I think we also have something to plot the digits, maybe not. Plot digits. The codings, right? So if we plot here those codings, so let's say plot, so let me see, plot digits. Where is plot digits? Yeah, plot digits, and we do those codings, 0. Oh, image ops is not defined. All right, and we'll probably have to put all of these dependencies in the same place. All right. Right, so those are my codings. So they go from, there are 30 digits from 0 to 1, and they're 30. And depending on when you load them, so like at what point or after what training, they change. All right, so let's actually just do one thing. I don't really know how this will affect or overfit or whatever, but let's say we, because this is pretty fast, we define the model, boom, we do this definition here, we train, summary, and then we're going to train for 10 epochs, right? So still the model always gets to the same place, right? 9932 accuracy, and that's 10 epochs. So we still have the same input. We could maybe take this one or this one, right? These are different sketches, and we pass that through this one that says it was on 10 epochs, and now we can plot our digits, right? It's slightly different than before. We generate an image, and now we predict. So this is slightly different than before. And you know, we could actually just comment this out. We're gonna take another image, so let's say image 80. So let's say input is going to be x train 40, right? So now we just do this, so you just get the input. You don't need to do a lot more. Input, All right, so this is our input, and now we can choose from here with a number. So we say the input is a sketch 42. We have that, and this doesn't do anything. This does something. Now we plot our digits, and now we reconstruct our image, which doesn't look anything like this at all. So I don't really understand what's going on with the dataset. It might be that it's overfitting, and it's just like learning something that it does something really similar for everything, for all the images. Yeah, so it doesn't seem like it's doing much. All right, so one easy thing that we can do here is, because we've used the same variable names, right? We can you have to think about this, right? We have 104 sketches, and the fashion MNIST dataset has 60,000. So that's probably one of the things why it is performing so much better, right? So what we're gonna do is we're gonna load that dataset. Now we're going, after all this effort to load our custom dataset, we're going to define here their dataset, so that we're gonna have the same xtrain xvalid dataset. I don't think we need this part, and we do need this one. So we're gonna load that. We're going to load our model. We're gonna define everything the same way, and we're gonna train for 10 epochs. Let's see how long this takes. This takes a bit longer now because we have a bunch more images. We have 55,000 images for training and 5,000 for validation. And you should be thinking, right? Like, now the accuracy is slowly going up. It's not as fast as it was going up before, right? So we can see here this number keeps changing, and that's good, right? This means that there is some actual learning that is happening, not just that we're overfitting on a data set and learning a few things. And yeah, I would be interested in seeing this network, how many data points it needs to give some information that makes sense. Let's try. I mean, I'm not sure if this is gonna work, but all right. So the model is trained. Now we can put input 14 here. That is this, that looks like a shoe. Also look that the dataset is inverted, so that also might make it learn in a different way. So we get the codings. We still get 5 out of the last 10 calls. Triggered tf function retracing is expensive. Tf function repeatedly, blah blah blah. All right, but we get our data, and now we get our codings, right? These codings make a lot more sense. It's a bit more granular. It's not just like a lot of black. And we get our generated image here. All right, so it doesn't look anything like it, but at least it's a shoe, right? So it's learned something, and it seems like we're able to reconstruct the output from what we have. Let's actually just train for 10 more epochs, and see where we get. Just to let you know, while that's training, these codings here actually represent this shoe. If we modify these codings, we're gonna get a different image, right? That's kind of like a puppeteer. Like, we have an image, we're encoding it into this image, and then we decode it back. So if we generate images like this one, we will get images like this. And there is a correlation, of course, because of the weights that the neural network has learned from the codings to the output. All right, so it seems like we're almost done. We have a bit more accuracy, not too much more. And we are gonna use the same input. I'm gonna do one thing. I'm gonna leave this here, and I'm gonna compare, so how the codings are different. They are almost the same. So I would say let's regenerate this just in case. Generate the codings. They seem to be almost the same. Let's see if the decoder has learned anything else, right? So we have the image here. We're going to predict, and now, so I'm going to put it here. So I'm going to regenerate a new image. And you see, I mean, I can already see some changes in there. So it's not, okay, and let me just double check something. Okay, cool. There is a slight change. I'm gonna say, right? I made an error. I made a mistake. So this has changed, right? So we can compare these two images and they're different. So there is something else that the network is learning while we're retraining, right? What is funny is that I forgot to change this variable here. So this should actually say input, because we were continuously using extra in 0 while we were visualizing here the number 14. So if I actually do this, right, now you're gonna see how the codings that we get, and I'm gonna take these helper functions above, the codings that we get are gonna be super different, right? That's something that I didn't realize and nobody realized because nobody told me. So you should have told me. And that's gonna change. All right, so look at the codings now. So these codings here are super different, right? These now do encode the shoe, right? What we can see is that we go to 0 and we plot that image. We indeed have something super similar to that boot that we were generating before, right? Which is, you know, it's super funny. So we're gonna go back to the shoe. I'm going to go back and generate the codings, and now I'm going to generate that shoe, and I need to predict before. So predict and generate that shoe. Awesome. So now our decoder knows how to generate a shoe that looks a lot more like that one, and not, you know, not what we saw before that was an error, right? So what this brings us, or where this brings us, is like, let's actually train for like 50 more epochs, something that's going to take a bit. And let's try to take the rounded accuracy up. Let's see how the network learns differently. And later we're going to go back. We're going to use the data set of the sketches and actually verify if there is something that is being learned. Because before, even though we were training, we were not changing the actual input that we were predicting with on the encoder, right? So the codings were not really changing. So I do still have hope that we are going to see some things there, and that this is going to improve a bit. All right, so maybe I can, yeah, no, I'm not gonna do that. All right, so yeah, maybe I can share an image or something on all right. Okay, so hello, who's online? I'd like to ask, like, if you're online, let me know. Like, I want to know more or less if this pace that we're going through is interesting, or you can grasp something if it's too slow, if this is something that you're interested on seeing. Yeah, because this, you know, the fact of doing this online is mainly for you to be able to ask questions and to tell me what you would like to see more of, or like any comments that you have. Okay, so let's see if there's any activity on the Discord server. So I showed it before, and you know, we've seen it many times. It seems like on the machine learning channel, live 38, my t-SNE plots. Whoa, awesome. Is this something that you've done today? I'm just curious. Or is this something that you had from before? This is super cool. These seem to be grouped by similarity, right? At least these are all like vertical. Yeah, I mean, I can see some similarity. Right, this is a really nice background. Yeah, so and raster fairy regularization. Okay. Yeah, I would definitely like to learn more about these methods. I mean, I don't know if this is a different method. I don't know anything about. Great. I love this. Thanks for sharing. I just realized you shared a few minutes back. Okay, so we are at epoch 34 out of 50. I'm gonna grab some. Okay, no, I sent a t-SNE plot on Discord channel and regularized version of the same images. Check it out. Yeah, so I'm checking it out here. So I shared it. Is this something you've done following the live stream today, or you had this from before and you're showing us? This is really awesome. I really like it. All right, and while Ricardo is texting us, I'm going to go back here. I'm gonna take a let me see. I've done it a few months ago. Yeah, this is really cool. I'm going to leave you with this while this is training really quickly, and I'm gonna be back in a few moments, and we're gonna continue looking at the autoencoder. All right, we're back, and we're gonna keep going. Cool. Okay, so this is the Discord channel. So I was mentioning before on the coding channel, you can ask general coding questions. That was for class, right? Class, clues. I don't know how to pronounce that. And yeah, so really cool. So whoever wants to go there. Okay, one thing before I forget, so you can play with this if you're watching this later. I'm going to make this one to anyone on the internet can view. So we're gonna copy this and we're gonna put this on the links on this episode. So this is Colab notebook, and this is t-SNE load data stacked auto encoder. But notebook. Cool. And Ricardo, do you have a link that I can share there as well for some of the projects that you've done? Okay, so let's go and see. We're loading, we've trained for, I believe, 50 more epochs, right? So we get an accuracy of like 94%, I think. And we're going to now, so here we get the codings for, I think, I don't know, might be 10 plus 50. So we can see those here, right? So the codings do change a bit. And now when we plot them, right? So these were the ones from before. So when we plot them, they're really different. And let's see what the generated image looks like now. So we put a block in here. Okay, so this is because it's for the other image. So we need to define this here, 14. We put this here. We plot our codings. We do this. What am I doing wrong now? Input. Oh, okay. So same error as before. So we left this on the old code. So that's why. Okay, that's why we were erroring here. All right. So we put the input. So we get the codings. These look a bit more like the ones below. These look back again differently, and now we predict, and now we plot. Okay, so we're getting, you see here stripe, and I would say it's hard to notice which one looks more similar, but this is a bit more refined because we've trained for longer. So I would say maybe this one. So this is like 10. This is 10 plus 50. Let me show you here. And this is the input. This is the original. So this is the actual input. So which one looks more similar? I'm not sure. Right, so I guess they're more or less the same. They don't really look that much similar. But yeah, I don't know. That's kind of one of the outcomes of today, right? So let's just put here. All right, so what I was mentioning before, so we try what I said, is that these codings, right, if we look at the codings, what they really are, they're not more than an array contained inside of an array. So we could get this here and we could say, okay, I want my codings to be, for example, ouch. So my codings could be an MP array with this data. And now we put in the codings, and now we get exactly the same, but this is float 32 type, and we could probably do that as type numpy as float. See, as type well, I'm not gonna do that. Let's just try out. So I get the codings this way. I plot them. They're the same because I just copied. And then if we predict, we get the image, right? So let's put that image below. So those are the same image. And I'm gonna bring these. Well, we'll leave them here. So we can probably remove this part. So now what I'm gonna do is I have these codings here, and I'm gonna copy them. So I'm gonna change them slightly. So let's say here we put, well, not slightly, let's change them a lot. So maybe we put here a 4, this is gonna be an 8, this is gonna be -4, this is gonna be 13, this is gonna be 1, right? So we changed those codings, and now instead of the one we have above, we have the one below. And when I generate the image, that is what happens, right? We've changed the things, and there are some parts of the image that still look the same, but by changing numbers, we're changing different features on this image. And you know, one can imagine that now if I do put this one here to 0, and I plot again, now we have just changed slightly something here, right? So instead of white, we get this gray. Well, instead of this gray, we get this white. And now I can predict again and generate the image, and now that changes back again and looks again more like a shoe. Just changing one number like changes the output a lot. And okay, so what we're gonna do now, we're gonna leave these ones commented just to make sure that we don't get confused later, and we just use the actual prediction function. And we're gonna go back. I'm hesitant to duplicate this, so maybe let's leave this part 1 fashion MNIST and duplicate this one. Maybe not. Let's just see. And comment to use fashion MNIST dataset instead. Right. So we comment this out, and now what we do is, okay, I'm gonna take out a few things that are open. So we comment that out, and we just want to go back to where we are. I think everything, right? So we don't really need to expand twice here, and we don't really need 2 codings, and we don't really need 3 visualizations. So what we're gonna do is that we're gonna go back here, we're gonna restart and run all. So this is gonna restart the runtime of our Jupyter notebook in Colab, and it's going to execute all of our cells once again. And yeah, hopefully we can see something with our data set, right? With our real data set. Okay, so this has trained. We're at the same accuracy that we were able to get before, but now we have an image that if I set here 60, right, we can see a different input. So maybe we can just merge these ones, because it doesn't, you know, we don't really care that these are just one cell. So we're going to remove these other 2, right? So let's see, 4, 5, 6. Okay, so this is kind of different, right, from everything else. So we're going to go and run that. We're going to run the codings, which are a bit different. We're going to do that and then that. Okay, is there anything wrong here that we've done? So input xtrain 6, input shape, expand dims, input 0, coding 0, codings. No, this doesn't seem like it's changing a lot, right? So if we go now with 16, we have the input. We're actually predicting on the input. We plot the digits here, so we're gonna plot the digits again, and they barely change. So we do this and we do this. Yeah, so this is changing, but it's barely changing. It's just learning like a real weird mapping. Maybe one thing that we can do here is, so we can actually train for 10 epochs once again with the other data set and see. Let's just make a cool experiment. So this would be xtrain. Let's do here, save this as xtrain sketches x valid sketches equals xtrain x valid. All right, so we're going to rerun everything. So we're going to retrain now and regenerate the images. All right, so we're training here. On the meanwhile, so let's actually look at what we need to do the t-SNE algorithm, right? I'm gonna take a look here at the book. All right, so it seems fairly simple. So we have t-SNE, the scikit-learn implementation, which is including a scikit-learn manifold t-SNE, and all we need to do is something like this, more or less. We're gonna do that coding before we go today, and let's see how this went. Okay, so we have these pans, and we get pans, which is pretty good. I mean, we have a lot of data involved in this experiment, right? We could get these again, like hand generated codings, which match these ones here, pretty similar, and we get this, which is a completely different output, right? Well, again, let's comment that out, and instead of getting an input X train, so we're gonna get an input X train sketches, and we're gonna get the 5th sketch, right? So now we're talking about this one, and one thing that I mentioned before is the inversion of those. So maybe I'm not sure if we can if we can do something like this. Yeah, we can invert the image, right? Okay, so let's actually put this separate. So we put other logic here, current dataset, or force custom loaded dataset. All right, so we are gonna load that, and we're gonna plot, so the input -1, so this would load the original image, and this one would load like a separate sketch, right? So the interesting part here is that we have images that correspond to my drawings and not to clothing. We want to see if we obtain the codings of one of my sketches, what is the corresponding image from the decoder that we're going to obtain, right? What type of clothing? I'm trying to get here something that has a bit more contrast. All right, this one, for example. So I think what we need to do is say here input equals 1 minus input to get it negative, so we don't have to do this here. And now we can do this. We can extract the codings once again, and we generate the image, and then we plot it. All right, so you can see, right, like it's activating that part here, so it's trying to make it into a shirt. And yeah, I don't know, not the best, but it's a good experiment. It's kind of activating or like encoding with one data set and then obtaining with another one. Okay, let's see. Yeah, I don't know. It's a bit of a weird experiment, but good thing is, if we just comment this out, we still have the proper data that we needed. So we have those shoes, and all that we need to do in order to account with or to use the t-SNE algorithm, which we've been waiting for so long, we just need to say, okay, from scikit-learn manifold, right? What we saw before, import t-SNE, right? So we import that library, and now we say, okay, our x valid, or like x, let's say x valid or x train compressed, because we don't, well, let's actually do x valid, because otherwise we're gonna have too many. We say stacked encoder predict x valid, and we do t-SNE equals t-SNE, so we instantiate this library, and then we do x valid to d equals t-SNE feed transform x valid compressed. All right, so I'm gonna run this, and this is, this is processing, and the next thing that we're gonna do is that we'll make a scatter plot with the x valid to the everything in the 0, x valid to the everything on the 1, c y valid. Do we have y valid? I don't know if I removed that before. Okay, so we need that now for some reason, and we just need here s10 cmap tab 10. Yeah, and these are the categories, because we know the categories, and we know that there are 10 different classes, so I'm not sure. Yeah, so scalar, shape, array of list of colors or color optional, scalar array like shape optional, the marker size in points. All right, cool, let's try this. X valid is not defined. All right, cool. All right, so this actually matches in some ways, kind of changing the axis what I have on the book. So I think maybe if I changed, yeah, it's changing something on the axis. I don't know why, but it matches what I have on the book. And yeah, so if we didn't really have the call, so the valid, right? So if we print here, just so you see y valid, and I take like maybe 10, right? These are the classes of the data, right? So we have here x valid, and if I take 10, you actually have the images, right? These are the images that we're supposedly plotting there, and then here we have the colors. If I were not to provide that, we'll just get a set of plots, right? And you have to think that those have similarities among them. So yeah, this is t-SNE, right? This is the basis of what we were looking at. I want to continue further with this, so continue looking at this a bit more, and developing this further, because right now we just see like plots here. We don't even see images or anything, and it would be good to like plot some images here, or like even have an interactive board where we display the samples. And yeah, what else can we do? Can I try once more? I don't really know if we're like overfitting or what, but let me comment this out once again and try with our other data set. All right, so we're gonna train for, this is super fast, so let's do 100 epochs, and we're not gonna have x valid this time, so we're just going to remove this part, and we're going to reset and run all. All right, so I'm almost wrapping up here, so I would like to open it to questions or to comments or anything that you guys want to share. I'm going to be leaving pretty soon. I think we're almost done with this. I'm happy that we got to where we got today, and yeah, we'll be, let me see, well, maybe I don't, but yeah, we're going to be looking at more dimensionality reduction algorithms. All right, so this goes here. Okay, so what does this mean? So x valid, I don't really want x valid here. We want the actual thing, which is yeah, so let's actually do here x train compressed, x train to the x train, and that should be it, right? All right, so it seems like it still is fitting some, in some way, these drawings by similarity. I don't know that they're that different for them to learn any other things, but you know, they're spread on space, let's say, and I really want to now see the plots in these individual sketches and see which ones they are. How can I so can I provide here a, like an array or something, one like 0, 1, 2? I don't remember now what the shape of this was. 84 with x and y with size 84. All right, so range, well, let's actually make a list manually. So colors equal that, and for E in range 84, colors append I. Colors, let's see. All right, so we get 83, and then we can put that here, colors. We get 84 colors. and that plots. All right, that is useless, right? But we're going to do something just at least to cluster them. So we're gonna say e equals 0 and e plus 1, and then when if I is greater than 9, I is gonna be 0, and j is gonna go up, so j plus 1. So we have less colors. No, not really. Oh no. All right, so let's see how those colors play out. Great, we have too many colors still, so we might just need, let's say we just have 3 clusters, so 84 divided by 3, that's 28, so is it 25? Right, we have now 3 colors, so it means that this is telling us that drawings that are not initially together, right? This is not the order. They're like being clustered in different ways. So maybe let's inspect now that X train to D. So subplot images in scatter matplot. Can we do this? That's another challenge. Okay, so I wish I could just grab what images were these ones. Okay, I'm gonna paste this link because it's pretty cool. And we can probably continue with this one. PCA and t-SNE. All right, so what do we have here? Manifold from t-SNE. Components to perplexity 40. Feed transform results scaled. Feed transform. Visualize scatter with images. Let's try to just copy paste this one, which you shouldn't really copy and paste code, but because we're finishing up, let's see if we get that stretch goal. All right, so we got this here and we have this. So plot, annotation, bounding box, offset image. What are these helpers from? Right. Okay, let's see. So we can define this. This one is another one that might be good. So visualize scatter with images. Let's see. Oh, that is awesome. All right, so copy pasting that goes for the web. All right, that's awesome. Okay, so we got a pretty good resolution image, I think, and I might be able to maybe pump this up. Can I reshape array into shape? Oh, reshape, not rescale. Okay, image zoom, let's do maybe 4 because these are too small. Great, this is pretty awesome. Okay, so maybe let's just do 2. I don't know why it is coloring with that. Ooh, this is looking super good. All right, we got it. So I don't think we're gonna get too far with this, but long story short, I think we got it. We got what we wanted. So it seems in some way, it doesn't seem like it learned too many different features. It does seems like the darkest ones are, or like the more infilled ones are on the bottom left. Yeah, I don't know. I wouldn't say there is anything specific that well, I mean, these ones are the ones that are from some like people. I'm here. Yeah, I'm not sure. I mean, but this sort of worked, and if we, I think it would be a bit crazy if we do that with a segment of the other ones. So this is pretty cool. I'm gonna save this image. We can plot that, share it, and I think it would be cool to get a subset before we go. Get a subset, and so let's do plot. Remove that one, and maybe, I want to make sure this doesn't bump when I go with the other full data set, but I think it's okay. So let's try to just copy. Okay, so this render Disney sketches, and we're now going to copy these and paste them. I don't know if I can paste them here. Edit, paste. Okay, so the question that is being asked, and I'm gonna put it here because I think this is super relevant, Sajid. So on skip slide, this would say if the images, if the reduced dimensionality images form the x value, well, like the x well, yeah, let's do it like x values, do we follow the same, do we use the same technique to get the y values? All right, there is a bit of a misunderstanding, or like maybe lack of clarity that I explained here. So okay, just trying to reiterate the question, and maybe I need to move this. Okay, so looking at this question, if the reduced dimensionality images from the x values, so if the reduced dimensionality images form the x values, do we use the same technique to get the y values? So I don't think so. We're not getting the y values. There are two y values that we're mentioning here in the stacked auto-encoder world. There is one x value and one y value, and in any other neural network that we're using for training. And then later in the t-SNE dimensionality reduction algorithm, there's also X and Y. The first ones that come from the Fashion MNIST dataset are the X and Y values from the inputs to a training neural network and the outputs when they're classified, right? So if you input a shoe, maybe the class is number 5. If you input a shirt, maybe class is number 8. So you have inputs that are images and outputs that are the classified images. In the specific case of stacked autoencoders, we're inputting the image and outputting the image. That's why throughout the workshop, we didn't use the Y values. We were using the Y values as the colors for which to plot the data with, right? And that's sort of like a validation that the t-SNE dimensionality reduction and the codings with the stacked autoencoders that we're obtaining make sense for this dataset, right? That they're actually being distributed by similarity. t-SNE is only reducing those 30 digits to 2 dimensions, right? So those 30 digits already represent similarity. If we could sort those 30-digit codings by similarity in a row, right? To the human eye, they wouldn't make sense, but if we plot the images, they would. What t-SNE does is that instead of having 30 dimensions, so they're not visible to the human eye, you go and try to plot them, right? So you squeeze those 30 digits, so 30-dimensional space, into a 2D space, which is X and Y. So we get those 30 numbers from the codings into 2D, that is X and Y. So the same method brings the codings from 30 digits to 2 digits, that is X and Y. The X train that we named before are the images. We don't have anything to do with the t-SNE dimensionality reduction algorithm. And the Y values that we were mentioning before were the categories of the data samples that we were plotting, that only served, as I mentioned before, to color the dots for each of the individual samples. In the case of the Fashion MNIST, right, the dataset is really segmented into shoes, shirts, boots, and many other things. And then when we plot them, as we saw before, we can actually see that the actual classes that are being rendered, right? If I go here and scroll up, we don't have it right now, but we saw it before where the classes actually match more or less the colors, right? But you can see that it's not exact, right? There are like colors here, like the blue and the pink only correspond to shirt, or I think maybe this other type of shirt, right? Where like these green, yellow ones are purses, but still their purses are getting mixed with these dresses, right? So, and even here, right? So yeah, there are two different X and Y, right? So X and this Y are different from the X and Y of the X valid 2D. This variable here, X valid 2D, that we can actually see with more resolution here, it's actually, so this one here, this is actually 2D values. These are images and these are just labels, right? So if we plot, as we were doing before, the X valid 2D, what we get is just and the notebook, yeah, we just get X and Y, X and Y, X and Y, and that's just to plot the values. And these come from the codings, right? We've encoded the X valid into compress, which this is like an array of codings, and if we print this one, we're gonna get like an array of 30-digit codings, right? And yeah, so that, I hope that that answers suggests a question, and thanks a lot for asking. I think this kind of wraps up conceptually a bit the last part of what we've done. Thank you. And for anyone who's watched, thanks a lot for watching, and I'll see you next time. It was Nono Martinez Alonso here. You can check out more of the machine learning videos on my YouTube channel. All right, so just to wrap up, thanks for the questions, Sajed. That was super useful. And the last thing that I want to do, probably I can delete this one. Can I delete this one? Move to trash. Copy off. Yeah. All right. So what we want to do, and I'm gonna close things here. I'm falling asleep now. We're gonna close these things. Yeah, thank you for the question. Really, that was really useful. And we're gonna come here to live. This is t-SNE sketches 105. Yeah, so that is here. And the fact that they're linear, I'm not sure. That might be because there are not more dimensions to separate them, more features for the dataset to learn from. And I'm actually gonna tweet live because I think this result has been pretty cool. Maybe I need to go out of incognito. All right. So right, that's just a call to action. See if anyone's online, and that should be now here. If anyone passes by, maybe they can say hi. All right, so where were we? As I said, I'm tired, but we're still gonna do this. Let's see. So we're gonna close this thing. We're gonna hide this as well. Reduction with t-SNE, render t-SNE sketches. All right. So we're just gonna copy all of this, and I probably don't need the colors. Yeah, I don't think so. Render t-SNE images of fashion MNIST. Okay. All right. So how are we gonna do this? We do have up there, so I can remove this. We do have this. We don't really need to print this anymore. We do have this. Put it here. Put this here. And we do want the colors. Well, we don't really need this anymore. We just need this really. And xtrain to d and xtrain. Maybe we're gonna have more images. Xvalid. Maybe let's just pick 500 images for now. And what else? We need to train the model, and that's going to take a bit of time. So let's put this back. Restart and run all. There'll be things that are not going to work, but we'll get there. And these probably the thing that's going to take the longest is going to be training, which is going to take like maybe 10 or 15 seconds. Oh, 100. Maybe not. No time for that. All right, so we restart again. All right, so we're running again. I think we're still using a GPU. And yeah, and as Ricardo mentioned before, you should get Colab Pro if you're going to be training models for long. Colab Pro. It's like $10 a month, so definitely worth it. All right, so we're training 6 out of 10. We're almost there. All right, I'll ask for whoever is online. Do you want to let me know on the chat what you want to see next time? So next Thursday, we are not going to have live streams on August for the most part. I don't think we'll have any. So next week is maybe going to be the last one unless I do others during the week. So yeah, let me know. Let me know. All right, so we should be now done with training. We are. Great, and we probably gonna see some error below, but let's see. Well, probably not. Oh, yeah, I don't think this is gonna get completed. This is too much to be plotted. All right, so I'm gonna interrupt that one because where I want to really get is here. So we do that and then visualize. Okay, and we run this helper, and then we run this cell once again. X train to the, X valid to the, all right, whatever. All right, and yeah, we should now get an image generated here. Great. And maybe, just maybe, so we do here CMap gray. We run that again, and we're gonna do that here CMap gray R. Awesome, great. This is indeed pretty cool. Okay, what this tells me is that, we haven't trained for long enough, probably. I'm gonna get more samples, so I'm gonna take 2,500. But yeah, so we can train for longer. It's already really late. I don't know for how long we've been going. 3 hours. Okay, so let's see. Maybe it's a bit too much. Okay, that works. That's a cool image, right? I don't think these ones are similar. Not sure if we're doing anything wrong here. Let me see if there's anything. So X valid, X valid, X valid, compressed, X valid, fit, X train. All right, X valid. Images. Okay, so we're X valid to 500, right? Right, let's see. Yeah, this is like, looks wrong, definitely. Okay, ha, that's so much better. That's awesome. Okay, so this is really cool. This is something more similar to what Ricardo was showing before. So this is awesome that just with 10 epochs, this looks so good. Okay, so let's parameterize this then, because this maybe we can do it even better. So we'll do input, it's gonna be this, and we'll just predict on the input, and maybe just put the inputs. All right, so what do we want to do? Okay, I'm gonna generate this just to make sure that we are getting the same. So 0 0 0 1. And what we're gonna do right now is I'm going to close this thing. So comment this out. This is being plotted, which is pretty cool. This has now changed. Not sure why it changed. For some weird reason. And we're just gonna train for longer just to see how that image actually changes, how the sorting changes. So we're gonna train here for 20 epochs. And when we have the model trained, these will be trained for 30 epochs total, and then we'll be able to get this thing. All right, let's start archiving a bit. So we have that on Discord. These images are gonna go into today's folder. Let's check that the images on the other data set are also right, because that might mean so we have X-train here, and we can put this helper function above. Yes, I think this was okay. So we have the X-train and X-train here. Yeah. All right, so we are at 17 epochs out of 20. Right, and now this should be running. So this is run, and now this is gonna run. All right, so this is the comparison moment. So we're gonna take a look at whether training for 20 more epochs is improving anything of our result. And maybe we have the axis changed again. I don't understand why. All right, so t-SNE doesn't give us the same axis all the time, which sucks. So I cannot compare. But anyhow, for some reason, this is not doing that. But yeah, this is great. So we're sorting shoes by similarity. So now we could create a recommendation system just with these images where if you pick this dress, you could propose a few other things that are around it. Great. All right, so this was live stream 38. I always start thinking that I don't want to go for so long, but then we end up getting into these things. And today was one of the only days when I chose a topic and we actually did the whole thing in one go. So thanks for being there. This has been awesome. We have the notebook there to check for everything that we've done. And yeah, I'll do one thing. I'm just gonna put the outputs that we've obtained on the on there, right? So this is so this is what we've done today, and this one. All right, and with all of that, if there's anyone who just connected, say hi, tell us where you're connecting from, and if you wanna, if you wanna ask anything. Otherwise, we're done here. It's gonna be, it's gonna be like, I mean, it was a pleasure. I have enjoyed this session a lot. Thanks for everyone's participation. I really hope that you're learning something as I am. So I didn't know any of, like, I mean, I knew what we learned on previous live streams, but I keep learning. So yeah, call to action. Support the channel by liking the video if you're enjoying, or if you just want to support the work I'm doing here, and subscribe if you want to get notified when I go live next or when I upload new videos. You can join the community. There is, I've repeated a bunch today. I want to thank you for watching, and I'll hopefully see you next time. On the meanwhile, you can go watch many videos that are already online on the YouTube channel. So we can see that at Nono.MA YouTube. I have plenty of material, plenty of videos. Also have the the Getting Simple podcast that you can take a look at gettingsimple.com. There's like 50 episodes already, many related with machine learning, others with design, art, creativity, and more things. And I'll give a shout out to Parametric Camp. If you want to learn how to do parametric design with Grasshopper, this is the place to go. Also a lot of C#, a lot of things. The computational design live stream by Jose Luis is something that you can learn a lot from. I'll give also a shout out to Major Mystery. I never find your channel, but I always look for it. So let's open Incognito here. You can look for Major Mystery. Well, this is not the one. Architecture. Yes, engineering architecture. You can go and follow his channel as well. And yeah, I don't know, a lot more to come. Check out Ricardo's work as well. And if you're watching, or if you're watching after the fact and you want to share your work, join the community. Go to the share channel, and people are already doing that here. They're sharing things. If there is something really specific, for example, as Ricardo did today, to share, maybe you can share on the machine learning channel, or as I did with some of the outcomes of this live stream. Once again, it was Nono Martinez Alonso here. Thanks a lot for being there. I would appreciate your comments. If you have any questions, any suggestions, leave them on the video comments. And yeah, I'll see you next time. Bye.